Hello, everybody, and welcome to today's webinar, EdgeML Energy Monitoring on the particle Photon 2 with Edge Impulse. From Particle today, we are joined by Sarah Musgriz, Alliances Manager, and from Edge Impulse, we are joined by Brennan Dayberry, who is our Solutions Architect. We welcome questions throughout the webinar, so please add these to the Q&A box, and we'll either answer them during the session or at the end. And with that, over to you, Sarah.
Hi, everyone. I'm Sarah, and thank you for having me today. So I am leading partnerships for Particle, and I'm here to help present on our portion of the presentation. Then Brennan's going to take over for the rest of it. So starting with just like the why behind Particle. So if anyone's familiar with IoT, which I'm assuming many of you are, most projects fail. Typically, it takes 18 months for an average product to get to market, and oftentimes you have to start over and over and over again. Going into the next slide, I want to talk about like how Particle comes into that and how we've been able to solve a lot of that for many of our customers. So Particle typically, by leveraging our platform, it takes 6 months to bring an IoT product to market. We're able to shorten that life cycle initially, and by leveraging our full platform, which I'll share a bit about, you can eliminate a lot of the management behind building the product, vendor management specifically, working with multiple vendors in order to find the right parts and pieces to build a working smart device. And by leveraging Particle's platform, what we call integrated, you're able to eliminate a lot of those pains around that experience. Now, this also helps costs go down, not only from a time perspective, but when you are in a proof of concept or a pilot phase, it's often very expensive because you are having to build multiple versions and test multiple technologies in order to figure out which one's going to work best. So we can help eliminate that by creating consistency across the board and allowing you to focus on tweaking the other things like the sensors or the applications that you're going to have Particle work with for the smart device or product that you're building. So in the next slide, I'm going to just share a bit about who we are, and then I'm going to get into more of like the technical details, and then we'll be handing it over to Brennan. So we've been in the market for 10 years now. We started as a Kickstarter. Our founder was building a smart light switch for his home for his father, who was deaf and couldn't hear when the doorbell was ringing. And that turned into a Kickstarter, which then turned into a business and who we are today. We are a very well-recognized leader in the market for IoT. We have logos like you see here, Fortune 500 companies that have trusted us since the beginning of product builds and has continued working with us all the way through to production. So these are, big companies that are looking to make their product lines more smart, and they're trusting Particle to do that with them. And we've continued having these relationships in the market. We don't do all of it for them, right? But there are smart lines that a lot of these companies are building, and Particle is at the heart of that. So in terms of like how we've grown and how we got to where we are today, we're loved by developers. That's a huge community for us. It drives a lot of our growth, organic growth specifically. And often we'll have the developers be the ones who are instilling us in a product build for many of our larger customers. So we have a wonderful community around that. And if anyone wants to learn about that, we'll share some information after this webinar. Moving into the next slide, please. Okay, so if you think about IoT and like building a project, the way we describe it to our prospects and to anyone that's working with our solution, the project itself is like the tip of the iceberg. Like building the project and understanding what you want to accomplish is just a small piece of that, but actually making that come alive is what you don't see. Often IoT is not seen, right? When you think of like a smart bike or an e-bike, or like a smart scooter, what have you, it's all enclosed, right? We're not seeing the brains behind what is allowing this device to become smart, and Particle is what you don't see. So moving into the next slide, I'm going to now open it up and kind of explain to you what that means. So we call ourselves an integrated IoT platform because we're able to address the edge to cloud infrastructure that allows you to build a smart connected product all the way from the device itself, firmware connectivity, and the cloud component. So we are not necessarily looking at this data and interpreting the data or actually reading it and taking it from the field. We are the carriers of it. We are taking it from A to Z, allowing for our customers and all of the people working with our platform on projects to focus on all the other things around us. This removes headaches. This allows for a more efficient process and repeatability from a reliability standpoint for building an IoT product. If we go into the next slide, I'm going to now share a little bit about how we solve the most common, I'd say, problems in the markets that we play in. We like to think about it from a business need perspective. Our platform is meant to be customized. It's meant to be opened up, but we also have off-the-shelf offerings. And what you're going to learn about today is the P2 and Photon product line. And that's what we are leveraging Edge Impulse's services for. Brennan's going to share more on the details there. But in terms of like the actual business need, you might have that product, the Photon itself, but it can do many different things. It's all based on what our customers or prospects need. So on the left side of this slide, you just see a few listed here, like asset tracking, monitoring, reducing cost. You use the particle device, and that unlocks a use case that can then go solve that business need. So it's kind of a circular motion, but with particle in the center. And so it really just depends on like what your objectives are for your project. And then we have different avenues that will be able to get you there. So next slide is, I think, the last slide, and then I'll be handing it over. Yeah, so just a little bit about our partnership. Before Edge Impulse, we did not have the ability to really run, we didn't have the ability to really, quote unquote, work at the edge like we do up in the cloud. The thing with Edge Impulse that allowed us, what it's allowed us to do is it's allowed us to have a lot more control at the edge. And by running the machine learning and AI applications, we can now make decisions at the edge as well. We have the ability to also deploy new models through the OTA system that we just deployed into all of our product lines. It's called, it's for over-the-air updates. So if anyone's familiar with what that is, that's a new product, a new feature we just released to our product, and this specific Photon and P2 can use that as well. And then also we have different types of use cases that we've already built out that people can leverage if they want as guides or as they're building their projects using the Edge Impulse and particle integration. There's reference use cases out there that people can leverage. I'm going to hand it off to Brennan now, who's going to get into more of the details on the technical side. And thank you for listening.
All right. Thank you for that great introduction, Sarah. I'm going to take it from there and show you just how easy it is to use Particle to do anything EdgeML related, but this is energy monitoring. So first, we always ask why use EdgeML? Why not do it in the cloud? The biggest reasons for that are shown here. We champion these whenever we can. For energy monitoring, the best one to go for is bandwidth. If you're monitoring tons of different things, devices all at once, you can't send the bandwidth for that and all of that up to the cloud. But more importantly, privacy. Energy monitoring has a lot of metadata about what people do in their private life. So it's not something you really want to be sending to the cloud all the time. If you can make those decisions and those inferences on the edge near the user, that really speaks more to privacy, and a lot of people won't even touch anything if their data is being sent to the cloud. They just won't even go near it. So it's very important to be mindful of people's privacy. There's some other reasons, cost, which also drives into bandwidth, and power, if you're in low power situations, if you're in an ultra low power device. Energy monitoring doesn't rely on that so much. So I'm going to say bandwidth and privacy are the most important reasons for energy monitoring. We work on any device under the sun. We work on ultra low power devices if you just want to do basic anomaly detection, all the way up to NVIDIA GPUs and really fancy AI accelerators. The Photon 2 is in this category, what I call a high-end MCU. It can do up to audio classification, but not quite much image classification. What we're doing on the energy monitor with energy monitoring could be done potentially on a low-end MCU as well. But the Photon 2 has quite a bit of memory and a good amount of horsepower for us to do what we need to do. So some use cases and applications here. A lot of what we do is in health. We work with a lot of health companies. So in this context, in hospitals, assisted living facilities, you can detect when things are on that normally shouldn't be on. If someone's up in the middle of the night, and especially in like a memory care facility, this could be very important, or just alerting emergency services when certain things happen. In a residential use case, you could do kind of what we're doing here with the demo, which is just residential devices to show a lower scale. If you're just trying to make sure that devices in your house are turning on or not coming on when they're supposed to, how you'd optimize your renewables if you have a source for renewables and you only want to use those when the renewable has power, and just reducing overall energy footprint. And then in the commercial and industrial use cases, load balancing for commercial cases, if you have certain events that happen at your facility, stadiums, you want to be able to predict that and balance when that happens. And then in industrial scenarios, predictive maintenance is always something that EdgeML is used for. And in this case, you're not monitoring, say, a bearing and the sound of a bearing. You'd be monitoring how often its pump turns on and off, or the duty cycle of something to say this is out of normal operating parameters based on its energy signature. And then some of the shared use cases, we have grid reliability for commercial and industrial cases, which leads into also smart grids for all of residential, commercial, and industrial. So utility companies could actually be using some of this technology at a much higher scale to see what categories of devices are on. If people are turning on certain appliances at certain times of day, they can help use that to better supply the grid at the right times and turn up the power sources when they need to. So the most useful thing I think that covers the other cases is usage alerts, because this can flag when devices turn on and off. So that covers health, residential, and commercial. And those are something that you'll see in a very basic form today, where we send data up to the cloud based on what devices are on and off. So we're sending the results. We're not sending the raw data, which is important. So how does this work? This isn't a DC power monitor, it's AC. Just to clarify, if you thought this did DC, it's looking at AC spectral content. So we're measuring the AC voltage and current on, in my case, a surge protector, but you could do this on an entire circuit breaker. You could scale this up even larger with the right equipment. But with the Photon 2, it makes sense to do it at this scale. So we are using the signatures of these devices and their combined states to characterize when they're on and off, and which devices are consuming power. And we're also very rudimentarily measuring the power, but that's not really the point. The point is the on and off states of the devices. So a little bit back to fundamentals of electronics and digital signal processing. A perfect sinusoid waveform is just made up of one fundamental, but if you have something like here, a complex waveform shown at the bottom, it's made up of many different components that you can break down into its harmonics. So what we look at in this is somewhat of the harmonics. There's also some spectral analysis that we do, but a lot of the features that we found important in our pipeline were the spectral density of these harmonics. So I like to use the analogy that when you're at a dinner party with someone, you don't have to yell at each other, because you know the sound of that person's voice. They have unique spectral features. Their voice has different powers and different bands. And so it's kind of the same of how we're able to pick the signal out of the noise with machine learning to be able to determine the same thing. How we do that first starts at the analog front end. This simply takes the AC signal, the voltage, and it uses a transformer for safety and also to bring down the voltage, and then puts that into one of the ADD pins of the Photon 2. And then we also have an input for a current clamp that uses, it's a magnet that goes a toroid that goes around cable, and then you can put that into an instrumentation amplifier, and then that goes into the other A to D pin of Photon 2. So this conditions these, and it puts these right around 3.3 volts so that the signals look like what you saw on the previous slide. We get our full scale at the range we need it to, and we're able to get good resolution on these signals. This is the layout of that board. Simple 2-layer board, a couple transformers, nothing too fancy, but in case you want to see the layout. Now we collect data. This is what's easy with Photon 2 and EdgeMPulse, and more so than any other way you're going to do machine learning. So we'll start with, these are the appliances that I used. You can see them here. We have a lamp, a desk fan, a mini fridge, a blender, and we have a toaster for our anomaly detection. This is a special power strip I got that has the line, neutral, and ground, so I can easily get at the line signal with the current clamp without having to take apart too much. So this is the current clamp we used. And then for sake of simplicity with the platform, we collected data for all permutations of the device, and it also kind of gives a good picture into their combined states. So it was a good exercise in data science as well. This is what the setup looks like. You'll see this a little bit later in the live demo, but you can see all the devices are here, the power strips here. They're all plugged into one power strip, and there's a current clamp just operating on one single point. We're not measuring these individually, because then what's the machine learning going to do? So this is a little bit of a diagram that shows the path of this. So we start down here at the device, the Photon 2, we go up through the particle cloud, and then we get into data acquisition. And we do this very, very simply. So this is when we talk, Sarah talked about the tip of the iceberg. This is the top of the iceberg, and Particle handles the rest. I usually don't like showing code, but this is how easy it is. It's a few dozen lines of code, and it all really happens here in particle.publish. I can use their device OS tools to very quickly take this data, read it from a pin, put it in a JSON array, and send it up. And I don't have to worry about any of the other stuff that handles that. Connects to my own Wi-Fi. It's great. This is the webhook in Particle that takes that traffic that comes through and forwards it to our API, our data ingestion service. A few custom things have to be put in here. The API key for your project. You have to set the header to have a few key points that tell our data ingestion service what's actually happening here. Again, very straightforward, very simple to set up. And then here it is in our studio. And this is to show just how fast, I maybe could have gotten faster, but this is twice a second. So this is me sending data twice a second through that entire path up to our service. And it's showing up just as quickly, not missing a beat. So that's how easy the data gathering process is. I was able to just change one line in the code and then run it, connect a different device, connect sets of devices, and then run this data ingestion and collect all the data that we needed for the project. This would have taken a lot longer without Particle and just EdgeMPulse, and it would have taken even longer if I didn't have both of those tools. So now we move on to the impulse design and model training. This is what we call an impulse. If you're not familiar with EdgeMPulse, this is a whole pipeline from your data all the way to the output. So this shows how the data comes in, if we do any digital signal processing on it, how the classifiers work. So this could be audio classification, this could be image classification. We have a bunch of different stuff you can select from. This is time series data. So we do a very basic classifier on it. And then we have our output features, which is all of the different permutations of states, whether or not there's anomaly, and if it's just an idle no-load condition. One thing to note here, this window size was chosen specifically because it covers what we're interested in, which is the whole signal. We need at least one period, ideally 2 periods of the signal in our window for this to work. If it's too small, we're not really looking at the feature we care about. And if it's too big, well, that's a different story. So I selected this to be a little bit more than twice of the period at 60 Hertz. So it's 40 milliseconds. It's exactly half the data I was able to collect. So there is some thought that goes into picking how you choose the windowing. Then we move into spectral analysis, which I'll get into in the next slides of what that actually is. We have a classifier. that then takes the output of the spectral analysis, because we're not just looking at the classifiers aren't just looking at the raw data, because that you could do that, but that doesn't make sense in this case, because the spectral analysis is what's really pulling out the valuable information about what devices are on. And then lastly, we again have our output features. So let's move through that pipeline. What does that look like? Spectral analysis. So in our case, we're interested in the harmonics up to the 7th, or about 420 hertz in the United States. If you remember your Nyquist theorem, we have to sample it at least twice that. And that shows over here why. If you sample it less than twice, you lose part of the signal and you don't capture that frequency. So for simplicity's sake, again, we used a 1 millisecond device OS timer, which gives us a 1 kilohertz sample rate. If you sample faster, you'd get a little bit better performance, but this was straightforward, simple, and it got us going. And then I do 1024 point FFT. What this does is if you don't remember FFTs, that's fine. It breaks it down into essentially what you see the chart at the right, where I have good resolution over this range, because that means I have 2 bins of resolution per hertz of frequency. So I have really good resolution in the frequency domain as to what these signals look like. You could reduce the memory footprint of this entire thing to use a 256 point FFT, but the performance isn't as good because you don't have as much resolution. And I can get into some of that optimization later. This is our feature explorer. This is after you've brought in the data, and really it's just to show dissimilarities in the data. Maybe you have data that is wrongly labeled, and it'll help you identify that. In this case, I want you to look at this area in the middle where you see a lot of gray overlapping green, or these blobs here. There's a lot of colors to look at here, but what that is these categories: blender lamp and blender fan lamp. And you'll see later a different visualization of that. But what that means is a lot of the data here is very similar. So the network classifier might have a little bit of trouble with those cases. What are spectral features? There's a lot of digital signal processing that goes into it, but for purposes of this discussion, the ones that matter for energy monitoring are spectral power. Kurtosis shows up a little bit, which I'm not going to get into the definition of that, but it's widely used in predictive maintenance and detecting faulty signals. And then RMS and skewness don't show up a lot. These are the 4 main spectral features that our spectral features block extracts from signals. And so you'll see when I go into the next slide where we calculate the feature importance for each category of classification, why I've shown that spectral power and kurtosis show up the most. If you want more information on this, we have a great documentation page on this, and that's linked to at the bottom here of this slide. This shows the feature importance for different categories. I picked a few, and I'm not going to go over everything on here. This is really just to look at a top-level view where you can see with the lamp, the fundamental spectral power showed up a lot, and really nothing else. With the blender, fridge, fan, and lamp, all 4 of the devices besides the toaster anomaly, kurtosis actually shows up on that one, which is neat, and RMS does as well, but it's still dominated by the spectral power and the fundamental and the third harmonic. You get into just the fan, and as you might expect, the fan is dominated by the power and the 7th harmonic. And then all devices at once kind of gets averaged out, and you see a lot of spectral power in the fundamental, near the fundamental, and then some kurtosis. So this is something neat to look at when you do something like this. You can go look at the feature importance for a lot of these different things, and it helps give you an idea of what your data looks like. Anomaly detection. So I didn't collect data with the toaster. That would have added 16 more permutations, and so we decided it'd be great to use that as an anomaly, because the toaster doesn't look like any of these devices. We picked these devices because they have, one's a lamp, one's a fan. They look different spectrally. This is our newest type of anomaly detection that we offer, a Gaussian mixture model. We have another one called K-means. This one works a little bit differently. You can see here, there's probabilistic bands of where your data shows up. And if anything falls out of this band in any of these regions, it has a higher anomaly score because it's more unlikely to be real data. And so that anomaly score is output in the data, and if we detect an anomaly, we act accordingly. And you'll see that coming up here. We have confusion matrices. So this is from training data, which is selected from 10% of your, or it's validation data selected from 10% of your training data. And then we also have testing data. So the training data, the accuracy is 97% overall, but you can see we have some problem categories, which are the blender lamp and then blender fan lamp. So some in the training data, about 10% of the time, the model confuses whether it's a blender fan or a blender fan lamp. And it's probably because the lamp doesn't consume a lot of energy and the blender and the fan are noisy. They consume a lot. So you can see in the testing data, a similar pattern shows up. I optimized it to bring these values down and improve this case as much as I could because the rest of the cases are great. But this was the best that the model was able to get, which you could see in the demo, potentially this case might show up. But we can improve that. So we have Eon Tuner, and one of the things I did with this model was I wanted to squeeze out that last little bit of performance here in my trouble cases. So what is Eon Tuner? It stands for Edge Optimized Neural, but it really breaks down to, we have a lot of stuff to change in these pipelines. Do I change this? Do I change the FFT? What about the learning rate? If I want to change one, then I have to change one and then kick off a job and then go grab a Snickers and a coffee and come back and then do it again. And I have to do that a bunch of times. And it takes a long time. So this Eon Tuner does it all in parallel, and you set your search space, you set the parameters you want to change, and then you click go, and then many hours later, potentially you come back and it's got all these different impulses and it's rated them so you can sort based on your performance on your training data, your performance on your testing data. Maybe the most important thing for you is how fast it runs. Maybe the most important thing for you is their memory footprint. Maybe it's accuracy. In my case, I wanted to improve the accuracy score for that specific classifier case, and I did. And so I was able to get that up to what you saw, about almost 90% of the test data. But this makes that optimization search a lot easier. You don't have to change one thing at a time and go back and kick off the job individually. So this is very useful if you're trying to squeeze out that last little bit of performance or decide what models trade-offs are worth it. Now you do that, very straightforward. We have code here, you set what you want to change. So in this case, you see I changed the FFTs. I had an earlier one where I had lower FFT values just to prove out that it was bad performance, and it was. Change the training cycles, how many neurons your neural network, all this. So this you can see the best three that I got in that category, because this was sorting by the performance for that classifier, and this is the one I ended up choosing. And these are the parameters that I went with. All right, deploying on the edge, where the rubber meets the road. So this is on-device inference. Again, showing the code to show how easy it is. We still just sample the same signals we were sampling for data collection, except now we have a function called raw feature get data, where we copy that into another format so that we can then pass that to our run classifier function. And run classifier, again, you just generate code, hit deploy in Studio, put that on the device, and then build your application around it, which is what I did here. So we run the classifier, we get the result. I have the states of these devices where I just update them based on the result. And then based on that, I also update the LCD. And what you see here are the timing values for how long it took to do the DSP, the inference, and the anomaly detection. You'll see this live shortly, but this is what it looks like on device. We also, again, send results instead of data. This case, we're sending it up to DataCake. It's a different webhook, a little bit simpler, but again, we're just forwarding the data to DataCake, formatting in the correct way that DataCake expects, which is shown here on the next slide. They have a simple decoder that you decode into fields, and then it shows up on their platform. This was also featured at Imagine 2023, so if you were there, this demo was there in all its glory, and this is some pictures of that. And thank you, Dan Kuba, for doing that demo. I also owe a special thanks to Chris Martinez. His Hackster.io project, appliances identifier, kind of inspired this one. and talking with Chris on this project and working through some things with him was great. So I really appreciate your help, Chris. And if you're interested in some of his projects, you can check out his links here. Now time for the live demo. I'm using Logitech software because it was the easiest to overlay some of these signals. Right. So you see the same demo setup here. We have the camera pointed at both the screen and the overall setup, so you can see this is actually me doing this here. So I'm going to go ahead and turn everything on. All right, screen comes on. The only thing that's plugged in right now is the fridge. I leave it plugged in for these because it's the easiest one, or the not easiest one to plug in and unplug. It's connecting to the cloud. It connected this morning, so this should take less than 30 seconds usually to get on my Wi-Fi and get connected. While that's happening, I'm going to turn this lamp on. If it doesn't connect to the cloud within a certain amount of time, it'll just show the display anyways. So there you see lamp on, fridge on. Let's go ahead and turn this on. Now the fan is on. I'll do another use case here. So you can see different permutations. And there's a little bit of delay on when I turn that off because I had to filter it because of quick changes. So I had a little bit of hysteresis there. And then let's unplug. Yeah, so I unplugged the fridge. Fridge went off. You saw the fridge go off. And then let's do a couple permutations here, just so you see them all. And then the trouble one is a blender fan lamp, if you remember. So we'll see if I get that 10% or it doesn't. So you can see there, that was one of those 10% cases where it was wrong. But in every other case, it's very accurate. So we could potentially improve that. I'm going to take this off of here so you can see the rest. So that's the rest of the Photon 2, the analog front end. And now I'm going to do the anomaly detection. It flashes all of them are on real quick first. I need to fix that. But now it says anomaly detected, danger Will Robinson. Cancel toaster, goes back to this. And then, so you can all see the data cake results. There it is. This is all showing up. So this is, again, live. This is what I'm reporting every 4 or 5 seconds. So turn the lamp off just now, and then it goes off. And then just for no load, everything's unplugged, and it's off. And that's the live demo. I'll leave this open. I think we can go to the Q&A now.
Great. Okay. So we had a question come through. Do you know of any application using your sound analysis to animal, bird, insect sounds to differentiate between species?
Species, potentially, because one of our publicly clonable projects is a hummingbird or a woodpecker detector. So it's not the sound of the species necessarily, but it's pretty close. And that's available if you go to our projects. You can clone that one into your own and try that out. I haven't
Oh.
done a lot with audio classification though, so there might be someone else. If you ask that question on our forums, that can respond with a more thorough answer.
Okay, and then some questions for particle. Can particle work with any application?
I know that was for particle, but I guess any application. What do you mean?
Yeah, that's all I've got.
Manuel, if you're on mute, do you mind? Thank you.
Yes, so particle, part of the core offering of our particle modules is their reprogrammability capability. So that means that they're suited for multiple type of applications, which can be leveraged in conjunction with EdgeML to apply machine learning to all sort of use cases, from industrial monitoring, from commercial applications, or residential, and so forth.
Great, thank you. Another one here. What is the average amount of devices people use for a pilot with particle?
So that varies widely depending on your target deployment, cost of your whole build structure. But what we typically see is customers will typically work with a proof of concept that's up to like 2 to 5 devices, and then potentially scale to a pilot that could be anything from 20 to even 80 or 100 devices before going to a first big deployment, say of 500 or more devices, right? So typically in the range of 20 to 50 is what we see with customers.
Perfect. And then following on from that, how can somebody buy one? And does that include EdgeML?
Okay, yeah. So I can link that in the Q&A section, but we do have a retail store where you can get our Photon 2 and a machine learning kit, which comes pre-loaded with a bunch of different sensors that are perfect to pair up with machine learning applications.
Amazing, thank you. Somebody else has asked, where can we find the webhook settings?
So would that be for the demo that Brennan just showed?
I can actually show that. Yeah. I have the webhook open here. Oh, I have the events open. Yeah, of course. Oh. It's in the particle console on the integrations on the left. I'm going to put in my code anyways because why not? So you can see it. It changed on me. All right. Security is important, everybody. I get two-factor authentication on everything. Still advocate for it. So this is where the integrations are at. Tab here, integrations. You can add a new one here. This is the one I used for data collection. And it shows the settings. You can go in and edit the settings here. And then this is the one that I used for data cake, but it's much more straightforward. It's just a target link. It doesn't have any special features like the EdgeML.
Brennan, will this code base and webhook integration settings, like the actual JSON structure, would not be publicly shared?
Yeah, so the code bases for those projects are already shared. They're on GitHub. We're going to send links out after this, and they're also in the bottom of the slides, which will be sent out as well. And then the integrations I'll add to a separate repo, or I'll just put screenshots in the README on those.
Okay, yeah, perfect.
Yeah.
And there was a question earlier about using EdgeML on other particle boards. If you just wanted to explain about where we're at with that.
Yeah, Brandon, so specifically support for particle-borne devices, so our Gen 3 and
Oh,
cellular
boron. I
devices.
thought. Sorry,
Yeah.
sorry. I thought there was we're
No
integrating
worries.
that right now. So that will be forthcoming probably in Q1 of 2024. But we're integrating boron right now as we speak. I thought there was a I thought that said particle board devices, so I thought that was a question for you.
No worries.
Somebody would like to know what power strip you use, Brennan.
The specific one I can add a link to for what we send out. Again, I just chose it because it was the line and neutral and ground were already separated into 3 cables that were just joined together that I could split apart with an X-Acto. I don't know off the top of my head the exact brand that I used, but I just searched until I found one that had the cable format that I liked. If you searched
Okay.
for desk clamp power strip on Amazon, you'd probably find this exact one pretty quickly.
Okay, and then another one, what sensors and impulse training are required, or can the Photon to handle that out of the box? This is in terms of examples of predictive maintenance for equipment monitoring when motors and bearings are beginning to fail.
Out of the box, we do support the microphone with Photon 2. So if you're using audio to classify those, then you would be able to just deploy the existing binary on the Photon 2 and set it up in your studio project to collect audio samples and collect the data that way manually, or you can use the data forwarder or the data ingestion service like I used with the Photon. I prefer to use the data ingestion API because the Photon already connects to the cloud very easily. So to me, that was easier than doing it over serial, although that's entirely possible. But
And somebody has asked what OLED board you're using for the display, but I'm assuming as part of this project, you get the kit list of everything that you've used.
we haven't put together an exact kit for the project. I can put together a bill of materials that includes that display.
Okay. And I think that is it for the
So
questions. Was there anything, Brennan or Manuel, you wanted to add?
yeah, so there's this question over the chat. Someone's asking if you could please go over again how to get the model into the Photon after you've trained it, Yeah, how to get the model back.
So I can show that very easily here. So this is the publicly available project for this, which the link will be available. But when you do this, you go to deployment. And what I did was do a particle library. So this deploys it as, and again, I can't click that here, and that's a public one. But when you clone this in your own project, you have a button so you can click deploy, and it builds it. And then shortly thereafter, you get a zip file with the entire library that implements your impulse. So you then take the particle library and you can load this in to create a new particle project from that and build on top of that like I did, or you can load it into an existing particle project that you have. So once you're done with everything you've gotten everything the exact way you want it, that's when you go to deployment and build the library. So that's how you get it on the device. And then when you copy that into your particle workbench, is what I used, copy that into the project, and it builds just fine.
Awesome. Thanks, Brandon.
Yep.
Okay, there's no more questions come in. So yeah, Brennan or Manuel, do you have anything else you wanted to cover?
That's all.
Yeah,
Okay.
likewise.
Thank you everybody for joining. There will be a follow-up email with the link to the slides, other resources between Particle and Edge Impulse that might help for any projects you'd like to do. So again, thank you very much, and join us for the next webinar soon. Bye-bye.
Thanks, everybody.